Sorry, should record that. And it's in the practice question section. Looks like number 17, right? Yes? I'm going to accept that as a yes. What they ask is what would be the first step in the dehydration, thank you, of cyclohexanol and sulfuric acid. So we tagged some keywords here. We got dehydration, cyclohexanol, and sulfuric acid, which I'm just going to write out as the formula. So a couple things to address with this one. Sorry, totally lost my train. Yeah, it's completely gone. I don't know where we're going. Oh, let's go back to the test itself. The test itself, you're not allowed to write on the test, but I will come in with tons and tons of paper. Okay? So the way we'll organize the test is I'll pass out Scantrons before the exam. I'll get paper out to everybody 5 minutes before we start. I don't want you writing anything on the paper at that point. And then we'll start the exam at start time officially. As soon as I start passing out the exams, you can purge as much information as you want, so long as you're not talking to anybody else. So as long as the class is nice and silent when I pass out that first exam, if you're in that back row or front row, I don't care where you are, you can dump as much memorization material as you want onto the practice paper. Okay, or onto that scratch paper. And I'm perfectly fine with that. That also said, you can use that as a tool. So if you then slide that piece of paper under your exam booklet, that's a pretty crappy tool. Okay? Keep it out and visible in front of you at all times so that you can then quickly reference it. Because in theory, when you first started the test, you were right. 30, 50, 60 minutes into the test, your brain is mush. You want something to look at where you know it's right. Okay? And you should be able to trust that. That's going to be whatever you decide to write. When I say the exam starts, you can write down whatever you want onto the scratch paper. Okay? So that is for your benefit, yes. You can't have your own notes, unfortunately. Okay? So it's just going to be whatever you decided to memorize, you can purge it. Because I don't want people, that's one of the worst things that I think can happen with this test, is people go through and just try and keep it all in their head, and they have to keep constantly thinking about it. The more you think about the test, the worse you will be. Okay? Think as minimally as possible. Have something that you can look at and reference so that you don't have to think about it. Okay? Periodic table will be provided for. I think it's in the exam booklet, and you've got it up on the walls. So no periodic tables. There's no outside information you're allowed to bring in. Okay. Pencil or an eraser, that's all you need. You won't need a calculator, and yes, model kit, just because Scottsdale allows them, I'll allow them. I think it's not allowed officially, but don't report me to ACS. I'll blame Scottsdale. They were official testers for the test too, so. So back to the point. Let's try and process some of the questions that we see within this. So when I first read that question, these were the keywords that I picked out of it. And so what I would immediately do is on my scratch paper, I'd have a number down next to it. So question 17, so I could come back and look at it. I see dehydration, I see the D, and I think,
take it away.
I'm looking at a minus, and I see hydration. Water. If you're dehydrated, what happened? You don't have any water in you. So if you dehydrogenate, or you dehydrate something, you're removing water. This is page 54 in the book, in that study guide. All right? This is one of those questions that I kind of warned you about. You have to worry about nomenclature with this. All right, why? Because they're telling you cyclohexanol, and you need to actually have that structure handy so you know what you're looking at. All right? Which makes this a little bit trickier because you're looking at naming what kind of a species. An alcohol, which we've sort of vaguely covered. At least is enough for what you would need within this test. So we're looking at an OH for our alcohol that is bound to what? A cyclic hex structure. So we're looking at cyclohexane, which has 6 carbons. Okay. What if it doesn't say cyclo?
And it's just 6 carbons.
Don't draw a circle. Okay. The cyclo is required for it to be a cyclic structure. Okay, and that will drastically change your results if you either forget to include it as a cyclic structure or you make it a cyclic structure. And the last part, it actually said sulfuric acid, but I wrote it out as the formula already. When you look at that reagent, what should you see? So a lot of good answers out there. The answer that I would fish for is H+, which is because it's a strong acid. Okay? So now that I've got these pieces out here, I know somehow water has to leave this structure, and I need to use the cyclohexanol and the acid. And what they're asking for is, shoot, I already got rid of the thing.
Step?
Pretty sure it said first step, which also would have been a good thing to write down. Okay? So, first step. We're doing a dehydration, we're losing water. What do you think is going to happen in this case?
The H, the lone pair from the oxygen is going to potentially graduate.
Take the hydrogen.
Let's say you didn't remember dehydration was a loss of water, but you remember it as an elimination. That's valid. If it was an elimination, what do you need to do? You need a leaving group. Okay, so one of the things you could think, oh, well, that just leaves. What's the problem with that?
It's not a,
How do you know it's not a good leaving group?
because it's going to have a negative charge?
Because you drew it out, and you see that OH minus is a horrible leaving group because it's a strong base. If you don't draw that out, you may not see that you have that as a bad leaving group. So that means that step can't occur. We'd have to go back and say, okay, what can happen now? And as you guys were already alluding to, the lone pairs from our oxygen will react with the hydrogen to give us a horrible looking structure, but it's close enough.
Sounds like an axe head.
Here's your axe head. With our cyclohexane. What can happen now? Now it can leave. Why would oxygen leave?
Because they don't want that positive.
It does not want to be positively charged. Getting back to drawing sloppy. And we've got our water molecule floating around. So at this point, we've actually covered all the bases. We didn't even finish the reaction, but we've covered as far as we need to. The very first step of this reaction is what?
Protonation.
Protonation of the alcohol. So we can now sort through the possible answer choices and say which of those matches protonation of the alcohol.
That's exactly it.
That's exactly what they say?
Yeah.
Oh, that's nice.
Protonation of the alcohol.
Okay. Does that work? This is a trickier question because this is technically involving alcohol chemistry, which we haven't really talked about. Where it's falling in that gray area is we have talked about good leaving groups and that water is a good leaving group and we could make an alcohol a good leaving group by turning it into water. Okay.
On the scale of trickiest questions on the test, where is this one ranked?
5 million.
Wait, what?
Out of 10? Out of 10, probably in the 7 range.
Oh, good.
6 or 7, yeah.
Good. Because I felt really good about this one.
And 10 being really tricky.
Okay. Let's see a number 10.
Let's see a 10.
Really where I think the tricky ones pop up is if we're looking at, let's see if I can come up with one here. I think it's actually in the book. If we've got this and we go through to form I need that.
Okay. BH3.
What is it, H2O2 and hydroxide?
Yes.
And water. And then officially you've got your THF. kind of a random note here. You'll notice that in most cases, people will use this kind of dot in between those. Anybody know what that means? Kind of, actually, yeah. That dot in between the BH3 and the THF is because the THF is coordinating to the boron. The boron has that empty p orbital. The oxygen from your THF is actually weakly coordinating to the BH3 to stabilize it. So it's the dot product. It's the product of those two with each other. Okay.
Yes.
Don't add too many more words. You're confusing me already.
So isn't the BH3 going on the right side of that? And then the hydrogen actually probably below the and then
So in this reagent or in this reaction, our BH3 acts as the our electrophile, which is our positive charge. If we go through and take a look at our alkene, which carbon in our alkene is the negative? Left or right?
Right.
the one on the right.
The right is going to be the most negative and our left will be the most positive because
Hybridization.
it has to do with the stability of the positive and the negative. Our positive charge is more stable on a more substituted position. Our negative charge is more stable on the least substituted. So when we go through to do the reaction, and this is, I'm going to intentionally draw it a little bit vague here to begin with. Okay. And then eventually that OH is traded off, or sorry, that BH2 is traded off. Right? Yes, no.
Right?
Oh. Yeah. We'll do stereochemistry.
Stereochemistry is where this question becomes tricky. For your answers,
Oh, it's
Yeah. There it is. Oh, okay. Well, still, I'm proud of you.
whoops.
Good job for having this.
This was definitely
forms the bond
practice
between the
one.
hydrogen and the BH2, right? Technically. Well, actually from here to here.
There was a BH3.
Can't come up with a third answer or a fourth answer.
D stands for.
So, with these answer choices,
Oh, H.
what's our answer?
What's our answer? I can't really.
So we've got those four possible answers for this. And this is where it gets tricky. You have to know the stereochemistry of this reaction, because they do kind of run under the assumption that if you see BH3 and H2O, that you know that you're adding hydrogen and OH. So they go through and they give you three answers that all add hydrogen and OH. Okay? Within those three, hopefully one you can eliminate. Well, within the four, one of those I think very clearly comes out as being not right. Okay?
What does that say? Pineapples?
That's all I could come up with. That's why I don't write ACS tests.
Who's putting pineapples in all the answers? And this one said Oreos.
So between the other three answers, you would have to remember a little bit about the mechanism, that your boron's the electrophile and goes to the most substituted position, and our hydrogen goes to the other, which means we can eliminate that one. We'd have to know the dynamics of our reaction when we use our boron, that our hydrogen goes to the most substituted position, or it does the anti-Markovnikov. Okay? Which means that third answer cannot be correct because it has the OH, or it has our new hydrogen at the least substituted position. Now we run into the issue, and this is where I think it gets tricky, because you really have to understand the mechanism. And this is one of those, boron does weird mechanism stuff altogether. All right, and we did talk about this one in class. The hydrogen and the boron are added on the same side of the ring, which means when we look at our intermediate, the hydrogen and our BH2 need to both be wedged or both be dashed. Okay? That means we would expect our hydrogen and boron to be on the same side, but do we have a hydrogen and boron? No. What happened? The boron gets cleaved off by the peroxide and hydroxide. So not only do you need to know the stereochemistry of that first step, you need to know the stereochemistry of the second step, which is trading out the BH2 for your oxygen. And as we talked about in class, it maintains or retains stereochemistry, which means when we get to our product, wedged and wedged.
What causes it to retain the stereochemistry when it's replaced?
It has to do with the boron itself and how that oxygen is interacting with it. There is I'm pretty sure I've got a mechanism in one of the older slides.
Okay.
My half A mechanism, looking with your peroxide here, the peroxide can coordinate with the boron, and then we have too many electrons around the boron, so the boron comes out, picks up that oxygen, and it's coming out from that exact same position. It's the same type of reaction that the boron did putting on the hydrogen originally, except now instead of transferring a hydrogen, you're transferring a carbon in that process to your oxygen.
Okay.
Okay. That is not the official mechanism. It is a lot more complicated than that, but that gets us pretty close. That at least gets us to the point where the stereochemistry is maintained, because everything is happening with that boron at the exact same instant, all in that same plane, which means as the boron's kicked out, that oxygen is replacing it in the exact same spot. It's not coming in from the backside. It has to all happen at that same position. So one of the things that the peroxide is facilitating as well. All right. Which means when we get to our answer, and I see your hand, what answer are we going to get?
Second one.
Should be our second one. And now your question.
So, can you not just look at those answers and like pretty much see right away that that's going to be the optimum choice? Because if you look at the new projection, the hydroxy and the methyl will be anti.
Ooh.
No,
It's just a
because that's
coincidence.
all dependent on the mechanism.
So it's a coincidence.
It's a coincidence that they are on opposite sides.
So it was a lucky guess.
So, and if you get it right, I don't care. Sure, good job. Well, I do care. You can't copy off somebody else that got it right.
But that's not always going to work.
That is not always going to work. It's dependent on the reaction itself. Yep.
It's too bad.
All right. And you'll notice, too, that we were able to eliminate pretty easily 2 answers right off the bat. Pineapples and some other weird one. Okay. Usually, one of the answers isn't pineapples, but it's usually so far out there that it just doesn't make sense. Okay. Like you have the alcohol. Here, let's come up with a, because I now thought of one. We could run this, get this as our product. They go through and show the methyl group, our hydrogen, and they put an OH over here. And so yeah, that's kind of what you can play is if it comes down to it, you can just say, okay, one doesn't match, you're now down to 33% odds. Got to be careful with that. The ACS test makers are aware of that trick, and there are some problems where they give you 3 answers that all look relatively the same that are also all wrong. Okay. But if you've got no other choice, then that's what you're working with. Okay. Which is one of the things too. What's our average score on the ACS test? 50%, because we can eliminate 2 answers pretty quickly with a basic understanding, and then you're left with a 50-50 choice if you don't understand the material. Okay. That's where that average is really coming from.
On a ring, on a chair, and they have this. There's equatorial, and then what's the other one called?
Axial.
Axial.
Yes. Where are your substituents? Where do you want your largest substituents, equatorial or axial? You want it in the equatorial position. Okay. Is that relevant for this question?
No.
Yeah.
Why not?
It's
I heard most people say no.
not.
It's a,
Because the
it's a
answers aren't shown.
cyclohexane, isn't it?
Yeah, the answers aren't shown that way.
If the answer doesn't show up that way, that's one good approach to this. Why worry about some extra information if it's not asking for it? Okay? So focus on the information you've got. Worst case, you get down to those two answers, you don't know what to do. Leave it at those two answers and move on. That's why when you write down your scratch paper, you write down the number of the question. So at a later point in the exam, maybe you come across another question that reveals that answer or reveals the appropriate arrangement of those two. You can now double back and say, oh, it's this one. Okay? Or you double back and say, hey, heads. Like heads and tails. Apparently that wasn't very good. Other questions?